Alright, so in this video I'm going to go over how to determine the shape of the molecule. So in your note packet you should have something that looks like this. This is not the same exact one that you guys have in your packet, but it's pretty similar. So it shows all the different shapes that the molecules have. So I'm going to be referring to this when we determine the shape. So in your note packet, you might want to refer back to that as I'm doing this. All right, so when you're looking at shape, we need to talk about valence shell electron pair repulsion theory. And basically what this means, or what this is electrons repel each other. So your atoms, when you make a molecule, they're going to separate as far away from each other as possible, so because they're repelling each other. So they're going to have certain angles between the atoms because they're repelling each other away. All right, so when you have an atom or a molecule, you have two different types of pairs of electrons. You have lone pairs, and then you also have bonding pairs. So a lone pair will look like this. So if I have this molecule here, this would be a lone pair. And then the bonding pairs would be the pairs that are being shared in between the atoms. So if you have a lone pair on a central atom, so when we're determining shape, we're really just looking at the central atom here. When we do this, you're going to count how many lone pairs you have and bonding pairs. And the lone pairs are very important because they're actually more repulsive than atoms are. So if you have a lone pair on your central atom, it actually pushes the atoms closer together than they would normally be. So it's going to reduce the angle between the atoms. Now, we don't care about the angle between the lone pair and the atoms. We only care about the angle between the atoms. So instead of this being 120 degrees, which is the angle that would separate these three atoms normally, it actually will be less than 120 degrees because of this lone pair. All right, so let's look at some shapes. All right, so the first thing you do is you draw the Lewis structure, and then you're going to count the number of lone pairs on the central atom, and then you're going to count the number of bonding pairs. Okay, so we're only going to count bonding pairs as one. So if you have a double bond or a triple bond, you just count it as one bonding pair. Okay, so that might be something you want to write down. So if you have a double or triple bonds, you're just going to count it as one. As one bonding pair. And then basically, if you can draw the Lewis structure and you can count, then you can determine your shape. So you just have to know the most basic shapes. All right, so let's look at this molecule first. So PCl6 with a -1 charge. All right, so first of all, I can see already this is an expanded octet because it has more than 4 atoms bonding to the central atom. So that means that the phosphorus is going to have more than 8 electrons on it, and that's possible because it's in the 3rd energy level or below. So that can happen with atoms that are on the 3rd energy or below, because then they can open up that D sublevel. All right, so P will go in the center, and chlorine will go around it, and you're going to bond all the chlorines to phosphorus because it's going to be an expanded octet. All right, so let's go ahead and determine how many electrons we have for this. Phosphorus, we have 5 electrons available, plus the 7 on each chlorine, and there's 6 of those, plus the 1 extra electron right there. So we have 6. All right, so we have 48 electrons here. All right, so remember, this 1 extra electron came from the -1 charge here. So I have 48 electrons. I'm going to make single bonds between the chlorines and the phosphorus atom. All right, and then I'm going to distribute the electrons to the chlorines. All right, so now I've got 2, 4, 6, 8 around each chlorine. And if I multiply that by 6, I'm going to get 48 electrons. So I've used up all my electrons. And brackets with my charge. All right, so this is my Lewis structure. And again, this is an expanded octet. So now what I'm going to do, I'm going to look at the central atom only. I'm just looking at the central atom. I have 1, 2, 3, 4, 5, 6. I have 6 bonding pairs of electrons. And then I have no lone pairs. So this is what I have. I have 0 lone pairs. I have 6 bonding pairs. So when I look it up on the chart, okay, so 6 bonding pairs, 0 lone pairs, that would be an octahedral shape. So, and the reason it's an octahedral shape is because if I were to actually put sides on each of these, like dimension, or each of these 3 atoms right here, I would actually end up with 8 sides. So if it had walls, essentially, it would have 8 walls, and that's why it's octahedral, not hexahedral or something like that. All right, so let's look at the next one. Let's look at sulfite. All right, so sulfite, let's count our available electrons. Sulfur has 6, oxygen also has 6. And then we've got a charge of -2 here, so we've got an extra 2 electrons. So I've got 24 plus another 2, I get 26 electrons. All right, so sulfur will go in the center, oxygen around it. All right, so now let's go ahead and figure out how many bonds I should be making here. So I know that sulfur wants 8, oxygen wants 8. All right, so I would need to have 32 electrons. So to get my number of bonds, it would be 32 minus 26. So it would be 6 electrons, so it will end up being 3 bonds. All right, so now I'm going to make my bonds. Then I will distribute my electrons to the oxygen atoms. So 2, 4, 6, 8. So that's satisfied. Move on. 2, 4, 6, 8. 2, 4, 6, 8. So now I've got made all my oxygen satisfied, but I have not used all my electrons because that's only 2, 4, 6, 8 times 3 would be 24. So I've got 2 electrons left, so leftover electrons go as lone pairs.
Ms. Holcomb, please come to the front office. Ms. Holcomb, please come to the front office.
All right, so now I can determine my shape. So I'm going to look at my central atom. I'm going to count my bonding pairs, 1, 2, 3 bonding pairs. And I'm going to count my lone. I've got 1 lone pair. All right, and then I'm just going to look it up on my table. So if I look it up on my table, 3 bonding pairs, 1 lone pair will be trigonal pyramidal. Okay, so what you'll see here is that it's trigonal pyramidal. So instead of the 3 atoms laying flat in a plane, it's going to be, the atoms are going to be pushed a little bit closer together because of that lone pair, and it's actually going to form somewhat of a pyramid shape. So it's called trigonal pyramidal. All right, so let's do the next one, BF3. All right, so count the available electrons. Boron's in group 3. Fluorine is in group 7. And you've got 3 of those atoms, so it's going to be 21 plus 3, which would be 24. All right, so now let's do the needed electrons. Well, boron's in group 3, which means it's an exception. So the exceptions are hydrogen only wants 2, groups 1, 2, and 3 only want 2, 4, and 6. Okay, so boron actually only wants 6 electrons, not 8. It's an exception. And then fluorine wants to have 8, and there are 3 of those, so it's 24. So you want 30 electrons. So 30 minus 24 would be 6. All right, and then divide that by 2. You get 3 bonds. All right, so boron goes in the center, fluorine around it. So 1, 2, 3 bonds. Now I distribute the electrons to the left, to the fluorines. So 2, 4, 6, 8, move on. 2, 4, 6, 8, move on. 2, 4, 6, 8, move on. All right, so now I have 24 electrons used up. 2, 4, 6, 8 times 3 fluorine atoms. So I've used my electrons. Fluorines are satisfied, and so is boron because it's an exception. So to determine my shape, I look at boron. I say, okay, 1, 2, 3, 3 bonding pairs, and 0 lone. Well, if I look that up on my chart, which you should be doing, you would see that this is trigonal planar. So basically, this one and this one is different because this one has a lone pair. That lone pair pushes those atoms down closer towards each other and makes a pyramid shape. Well, with this one, since there's no lone pair, those atoms are actually going to sit flat on a plane. And then my angle between those atoms will be 120 degrees, and here it's going to be less because they're pushed closer together. All right, so you need to make sure that you know those basic shapes. You will not get that chart on the AP test, so you need to know those.